topic map of climate change, where we've been spending most of my time up in this top part of the topic map. So fossil fuels causing increases in CO2 concentrations in the atmosphere, that changing the Earth's energy budget and the Earth's global temperature. And now I'm going to be moving down into this portion of the diagram of thinking about how this then influences changes in weather and climate extremes. So I have down here 7 different topics. So tropical cyclones, fires, like forest fires, heat waves, cold spells, kind of two sides of the same coin, temperature extreme changes, extreme precipitation / thunderstorms / tornadoes, and then floods and droughts. And then floods, you can think about kind of multiple kinds of floods. There's floods in rivers, there's floods near coasts. So sea level is going to affect floods near coasts quite a bit. So we're going to be using the IPCC reports and their assessment of the scientific literature when we're talking about our understanding of climate change and its influence on weather and climate extremes. So these are some of the more recent IPCC reports, the Intergovernmental Panel on Climate Change. So these are our most authoritative, most consensus reports on our understanding of the science of climate change. So the last major, they're called synthesis reports, or the major reports that come out every about 7 years. The last one came out in 2014, and there's one coming out soon, probably 2021. Again, so it'll be interesting to see how language gets updated in those reports coming up this spring. But these are the most recent ones that I'm going to be pulling from in this for these topics. So before we get into what they say about extremes, these events, let's first compare that to what they say about global warming or global climate change. So here's a couple high-level conclusions from the IPCC reports in terms of this section of the diagram, the fossil fuel connection to global temperature section. So it says anthropogenic greenhouse gas emissions have increased since the pre-industrial era, driven largely by economic and population growth. So actually, I'll just highlight that. What is this? Economic and population growth. Have we talked about those two things in the context of any equation or identity? Yeah, so those are the first two terms in our Kaya identity, right? And then the other ones are the efficiency and the CO2 emissions. So energy efficiency and then CO2 emissions per unit of energy. But yeah, the greenhouse gas emissions have increased because of economic and population growth and are higher than ever. And so that's another thing to kind of think about, is that higher than ever. What's higher than ever? Emissions are higher than ever, not concentrations of greenhouse gases. So there's been times in the past when concentrations of CO2, for example, have been higher, but human emissions are higher than ever. This has led to atmospheric concentrations of carbon dioxide, methane, and nitrous oxide, or other major greenhouse gases, that are unprecedented in the last 800,000 years. Their effects, together with those of other anthropogenic drivers, have been detected throughout the climate system and are extremely likely, we'll come back to this language, to have been the dominant cause of the observed warming since the mid-20th century. So this is a very authoritative, direct statement that humans are increasing greenhouse gas concentrations, and those are warming the climate. And so it's an attribution statement also. It's not just saying that the climate is warming, it's attributing that warming to increases in greenhouse gas concentrations. Now, if you just separate the warming by itself, warming of the climate system is unequivocal. So there's no doubt the climate system has warmed since the 1950s. Many of the observed changes are unprecedented over decades to millennia. The atmosphere and ocean have warmed, the amounts of snow and ice have diminished, sea level has risen. So these, in terms of this portion of the diagram, very, very high confidence. We know to a high degree of scientific certainty that this is pretty straightforward. In terms of extreme events, this is one of those types of statements from the IPCC reports for extreme events, for weather and climate extremes. Changes in many extreme weather and climate events have been observed since 1950. So observed doesn't necessarily give you an attribution statement. It doesn't necessarily say it's attributed to increases in greenhouse gases. Some of these have been linked to human influences. So there's your kind of attribution. Some have been linked to human influences. And those include decreases in cold extremes, increases in warm extremes. So that's relatively straightforward. As the temperature on average warms, then we expect decreases in very cold temperatures, decreased frequency of cold temperatures and increased frequency of very warm temperatures. Then we have an increase in extreme high sea levels. So as ice melts and the ocean expands because it's getting warmer, sea level is rising, so that makes perfect sense. An increase in the number of heavy precipitation events in a number of regions. So it's interesting, kind of what's left out here is you don't see in this statement anything about tropical cyclones, anything about forest fires or fires, anything about thunderstorms or tornadoes, or like river floods or droughts. So we have what's made it into the kind of authoritative statements in the IPCC reports are heat waves, cold spells, some regional changes in extreme precipitation, things having to do with sea level. So that kind of gives us a clue here that some of these extreme events are a lot more complicated than just the global temperature is. And so that's one of our main themes that we're going to be talking about today. Here's a diagram from the IPCC report that basically kind of summarizes this statement, showing showing what weather and climate extremes are that we can be confident are changing. So increases in hot days and nights, warm spells and heat waves, decreases in cold days and nights. And then we have some regional statements about droughts. Droughts in the Mediterranean and are increasing, cold days and nights decreasing. So droughts in North America and Northwest Australia decreasing. So those made it in. And again, we see heavy precipitation events. And then we see, they do mention tropical cyclones here. Strongest tropical cyclones in the North Atlantic have increased. And these are not necessarily attribution statements attributing them to increases in greenhouse gas concentrations. They are just kind of trend statements. So looking at observations. So that's kind of giving you the headline first in terms of what the IPCC report can say or does say about weather and climate extremes. And so thinking about, some of the things that are left out, we can consider this diagram, which gives us an idea of the relative confidence in attributing different extreme events to increases in greenhouse gas concentrations. And so we have on our x-axis here how well we understand the likely influence on event types in general. So how well we understand this influence on the thing that they're talking about. And then on the y-axis, we have ability to detect possible influence of global warming on specific event. So that's, when we actually look at observations, how high quality our observations are, and how well we can model these things. And so how well we can actually detect a change in those things. And so we see, like, up here in the top, these are the things that we're going to have the most confidence in. So extreme heat, extreme cold, those are the ones that we saw make it into the authoritative statements in the IPCC reports. So those are up here. And then we go kind of down and have less confidence down here. So tropical cyclones, extratropical cyclones. So that's like the storm that we're experiencing right now in San Jose. Things like tornadoes would be severe convective storms. Wildfires are down here. So that's why you're not really seeing statements about these types of phenomena in the IPCC reports yet, at least. So I want to talk more about what makes it kind of complicated to make authoritative scientific statements about some of these things that are down here, why we have low confidence in some of these things. So I'm going to use tropical cyclones as an example of that. So just so we're on the same page, tropical cyclones, we call them hurricanes in the United States. But they also include what are often called just tropical storms. So difference between a tropical storm and a hurricane is just wind speed. So if we have a cyclonic storm in the tropics, so this is where they've all occurred over some historical period, I think 30, 40, 50 years. This is all the paths of tropical cyclones. If one of these storms is 39 miles per hour or greater, then we call it a tropical storm until it gets to 74 miles per hour, and then we call it a hurricane. And then we have these different categories of hurricanes: 1, 2, 3, 4, 5, where 5 is the strongest. But these are the things that, Hurricane Katrina, things that hit the Gulf Coast and the U.S. East Coast. And then they're also called hurricanes here, but then we call them typhoons over here, and cyclones in the Indian Ocean. They have different names, but they're the same physical phenomena. And you may have heard that this year is a record year in the Atlantic in terms of the number of tropical cyclones that have occurred. So we name these storms according to the alphabet every single year. So every year, the very first storm of the year is named with an A, and it goes B, C, D. And so if you run out of letters, which hardly ever happens, then we go to the Greek alphabet, the Greek alphabet. And so we're out of letters this year because we're up to 31 storms. So the storm that's hitting Nicaragua right now is Iota. So we're A, B, C, D, E, F, G, H, I, so we're way into the Greek alphabet right now. So record year in terms of number of tropical cyclones in the North Atlantic, which you'll see lots of headlines kind of attributing that to climate change, which is interesting because we're going to see that that's actually not a prediction in the IPCC reports, that we should get more tropical cyclones. So again, I'm using this. We're not actually going to talk about tropical cyclones per se in terms of exactly what the connection is between greenhouse gases and tropical cyclones, but I'm going to use them as an example of why, I guess, an example of the challenges of connecting increasing greenhouse gases to some of these weather and climate extremes. So let's go back to the IPCC reports and see what they have to say about tropical cyclones. So this is from the last major assessment, and it says, there is low confidence in attribution of changes in tropical cyclone activity to human influence, owing to insufficient observational evidence, lack of physical understanding of the links between anthropogenic drivers of climate and tropical cyclone activity, and the low level of agreement between studies as to the relative importance of internal variability and anthropogenic and natural forcings. So we're gonna come back to these. I'll just show you a couple more. This is from the one from 2014. So since then, there actually have been some increases in the confidence and in the authority of these statements. So this is a more recent one. Anthropogenic climate change has increased observed precipitation, medium confidence, winds, low confidence, and extreme sea level events, high confidence, associated with some tropical cyclones, which is increased intensity of multiple extreme events and associated cascading impacts, high confidence. And then it kind of elaborates, anthropogenic climate change may have contributed to a poleward migration of maximum tropical cyclone intensity in the Western North Pacific. So saying something about the spatial distribution of where tropical cyclones are occurring in recent decades, relative to anthropogenically forced or related to anthropogenically forced tropical expansion. So saying that the tropics are essentially getting bigger and moving some tropical cyclones to the north. And then there is emerging evidence for an increase in the annual global proportion of category 4 and 5 tropical cyclones in recent decades, low confidence. So saying that a larger fraction of the tropical cyclones that do occur are very strong, or there's some evidence of that anyway. And then here's one final pull quote from these reports. Based on process understanding and agreement in 21st century projections, it is likely that the observed frequency of occurrence of tropical cyclones will either decrease or remain essentially unchanged, concurrent with a likely increase in both global mean tropical cyclone maximum wind speed and precipitation rates. Okay, so that's an interesting statement. So they're saying that the projection is to get less hurricanes, but when they do occur, for them to have higher wind speeds and higher precipitation. So that would mean that seeing more and more frequent hurricanes like we saw this year would not be in line with this projection necessarily. The future influence of climate change and tropical cyclones is likely to vary by region. So some regions it could cause increase, some regions it could cause decrease. But the specific characteristics of the changes are not yet well quantified, and there is low confidence in region-specific projections of frequency and intensity. So as you can see, these paragraphs from the IPCC reports are very different than the paragraphs that are just talking about increases in greenhouse gases causing global temperature to increase. And so that's the main thing that I'm pointing out here, is that there's a lot of complications connecting this part to things like tropical cyclones. And so then you can get very different, headlines in the media, very different narratives depending on the sources of media that you're consuming. So one kind of example of something that's connecting very directly greenhouse gases to tropical cyclones would be the cover of An Inconvenient Truth, which has a tropical cyclone coming out of smokestacks. So that's a good visual direct connection, right? But you'll also see various stories and headlines in the media that say things, or at least are along this type of theme. No, hurricanes are not bigger, stronger, and more dangerous. And so I want to kind of dig in and see where this type of conflict could be coming from. So Roxy says, why would they say statements if they have low confidence? Well, okay. So first of all, let's talk about what they mean by low confidence. So thanks for that question, because this is one of the things I want to talk about. So the goals here are, first, over the next 4, 5, 6 lectures, is to actually understand some of the kind of physical background that connects increases in, for example, temperature to tropical cyclones or to all these different things. So understand the connection between anthropogenic greenhouse gas emissions and changes in weather and climate extremes. So that's one thing. But then also today, especially, I want you to understand kind of how climate science works and how it progresses. And we're going to, take a little bit of a look under the hood of, where these statements come from and why we would have low confidence or high confidence in various statements. And then one thing that I'll come back to probably more next semester is just to think about, some of the tensions that exist in terms of communicating climate science, where there's clearly, I think, a tension between being an effective communicator and an accurate communicator of science, right? Like that this could be seen as very effective, but it's not necessarily that accurate compared to looking at what the IPCC reports actually say about tropical cyclones. I mean, it's debatable, it's subjective, because there is certainly a connection between increasing greenhouse gas concentrations and tropical cyclones. Like that's beyond any reasonable doubt, that like no one would suggest that changing temperature has zero influence on hurricanes. It has to have an influence. It's just like temperature is very much a fundamental variable that affects all weather systems. So it'd be impossible for increasing temperatures not to affect tropical cyclones in some way. But as we can see from some of these statements, it's not exactly clear exactly how that effect is playing out. So that's just something to consider. So some of the the prerequisites for understanding this connection between temperature and extreme events would be to think about this question that was brought up about the definition of likelihood and of confidence in various things. And then also thinking about the definition of climate change in terms of these phenomena, different ways of quantifying these phenomena. So with temperature, it's very, very straightforward. You quantify temperature with thermometers that tell you the temperature, right? And so if you're talking about like increasing greenhouse gases, increased temperature, there's not like a million different ways to define temperature. There's just temperature. But when you're trying to quantify some of these other things, you have to kind of come up with a definition ahead of time. Like a tropical cyclone or a hurricane, we have these kind of arbitrary human produced definitions. We say like, oh, it's a tropical cyclone if the wind speed is 39 miles per hour or higher, or it's a tropical storm if the wind speed is 39 miles per hour or higher, and it's a hurricane if the wind speed is 74 miles per hour or higher. Those are made up by humans, and so that goes into kind of how you would quantify changes in these things as you think about like, what if you change the definition? What if you change the definition that it has to be 100 miles per hour or higher? Would you get a different answer? So that's one of the complicating factors. And then just our tools for understanding, which goes back to our pillars of science. And so these are kind of the 4 things I want to talk more about today before we get into the specifics of these things in coming lectures. So first, I think the IPCC does a really good job of laying out rigorously what they mean by likelihood and confidence of of various scientific statements. So this is some of their diagrams here on the right side that lay out what they mean when they say different things in terms of likelihood and in terms of confidence. So this white to black scale over here is their confidence scale. And so they kind of break this down into two dimensions where they have evidence on one dimension and then agreement on the other dimension. So evidence, which they say, okay, type, amount, quality, consistency. So various types of evidence. So you could have different kinds of observations, all showing kind of the same thing. You could have modeling, also showing the same thing. And so if you have many different kinds of evidence that are consistent, then you would have robust evidence, they would call it. And if you then have very high agreements between various kinds of evidence, then you can have high agreement and robust evidence, and so then you have high confidence in that thing. So you want to be on the upper right portion of this diagram in terms of being sure about something. And then when you have high confidence about something in terms of the IPCC nomenclature, then you'll get statements like virtually certain or very likely or likely. So they say a level of confidence is expressed using 5 qualifiers: very low, low, medium, high, and very high. It synthesizes the author team's judgments about the validity of findings as determined through evaluation of evidence and agreement. So this goes back a little bit to what I was talking about last time with the scientific method, that I do think that there's kind of a public misunderstanding about the scientific method, that they think it's just one thing and you can just do it and then the conclusion comes back and then that's science, and then then it's over, like we figured that out. But you can see here that really it's much more about like weighing evidence. It's the author team of the IPCC looking at all of the published papers that have come out in the last 7 to 10 years, and they're saying, well, this one says this, but it's looking at it this way, and this one says this, but it's looking at it this way, and so how can we reconcile that? And and it's basically a consensus like discussion, and there's subjectivity involved, but that's where these statements come from. It's subjective kind of weighing of evidence, and saying, okay, if we have multiple studies all pointing to the same thing, but they use different methods, they're relatively independent, they're using different models, they're different groups from different places around the world, and they're saying the same thing, then that's very, that gives you high confidence in a statement. Another thing is thinking about the definition of climate change and how it can be slightly more challenging to define climate change when you're thinking about these weather and climate extremes compared to when you're talking about like global average temperature. So just like take 30 seconds to a minute and think about, and possibly just write down on your notepad, how would you define climate change? Thinking about climate change in the context of weather and climate extremes. And what would be the best way to measure or confirm that climate is changing? Again, in terms of these extremes. And I'm trying to get at that it's harder to do it for this than it is for global average temperature. So I'll give you an example of kind of probably like the cleanest way to think about defining climate change. So going back to kind of one definition of climate change that I think is useful for thinking about this is, so climate, I've so far only been talking about climate change usually, I guess, in terms of the average of some variable, so the expected average. But another important part of that is the average variability of some variable like temperature or precipitation. So climate at any given location usually should encompass both the average and the variability of something. And in terms of contemporary climate change, what we're thinking about is, or at least one way to conceptualize it, is to think about like two states. So we're comparing the climate at some location under two states. And those states would be one where we're thinking about it like it's some hypothetical perpetual climate under the conditions of pre-industrial greenhouse gas concentrations. So pre-industrial, so prior to the Industrial Revolution, there was 280 parts per million of CO2 in the atmosphere. And in order to get at like the climate, you kind of have to imagine that everything else is just held constant. Everything's held constant. We kind of still have weather systems, and you still have just variability from day to day and from year to year. And that's going to kind of fill out your probability distribution of all of the various things that can happen. So that's why this perpetual word comes in, is you're just imagining it forever in some state. And then we're comparing that to a hypothetical situation with elevated greenhouse gas concentrations. So in this case, what typically is done is you think about what would the climate be like if you just had perpetual conditions where CO2 concentrations were double 2 times pre-industrial levels. So if you double 280 parts per million, you get 560 parts per million. And so you're kind of thinking about what is the climate, the global climate or the climate at any given location under these two scenarios. And so whenever we're talking about like trends in some variable over time, we're implicitly trying to get at this. We're implicitly trying to get at like, how is the underlying climate changing? But it's this, the perpetual part is thinking about that you could have a 1 in 1,000 year event, 1 in a million year event. Like those things exist and they happen. But it's like, it's hard to think about those if you're just talking about like, well, greenhouse gases are increasing and they're only at, 400 parts per million for 1 year, and then they're continuing to go up. So anyway, this is just, this is a hypothetical but clean way of thinking about what climate change is. And so then you can think about how a variable might change under these two climate scenarios. So under these two hypothetical climates. So we think about like daily high temperatures at some location, and we're usually thinking about things in terms of like probability of occurrence, that there's some element of randomness going on. So here would be, kind of like a bell curve, kind of like a Gaussian distribution of temperature that might occur at some location at 280 parts per million of CO2. And then we're comparing it to some climate at 560 parts per million CO2. So this is showing that you're warming the mean. And in this case, you still have this randomness. You still have, sometimes it's colder and sometimes it's warmer, but now your mean is higher. And the kind of average variability in this case has stayed the same. It wouldn't have to be like that. So it could be that your distribution kind of changes shape, and we'll talk more about that later, where it could change shape and you could get just as many cold extremes as before under your new climate, and then way more warm extremes or less warm extremes. So all sorts of things could happen. And so this is just something to keep in mind when we're talking about like the statistics and the change in extreme events. So temperature is the easy one to think about. But if we're talking about something like tropical cyclones, then it would be, you could, instead of degrees Fahrenheit down here, it could be wind speeds in different kind of bins. And it could be that certain that the probability of occurrence of a given tropical cyclone with a low wind speed maybe changes in one direction, and with a high wind speed changes in another direction. But it's just very hard to get at that when you have, 30 years of good satellite observations, for example. Okay, so that's just something to keep in mind in the back of your head, of like a definition of climate change would be a perpetual state under two different sets, two different levels of greenhouse gas concentrations in the atmosphere. And so you want to think about how everything changes under those different levels. Okay, so other things to consider when thinking about weather and climate extremes are the different ways to quantify these events, and then the tools for understanding them. So I want to revisit those paragraphs with some of this additional kind of scaffolding there. So what I'm going to bring in here is some different concepts here. So one is our columns for understanding that I talked about last time I lectured. So, understanding of a phenomena, I said, was built on observations of that thing, basic theory, and experimentation. So observations would be like just seeing how that thing has changed over the past 30 years, trying to quantify that as best that you can. Basic theory would be our kind of physical understanding, our theories, our equations for why a phenomena exists in the first place, and then why something like temperature might change that thing. Experimentation is harder for these situations. We can't go and start a tropical cyclone in some location and start it in another location and compare them. So you can't do experiments on tropical cyclones like that. We can kind of do that a little bit with fire. So there's prescribed burns that will start fires in different environments and see how spread rate changes and things like that. So experimentation kind of comes in with some of these and sometimes not. You can kind of mix observations and experimentation, because you can say there's something called a natural experiment where, like, let's say a given year happens to be very cold in the North Atlantic just because of random variability. And then you can say, oh, here's a natural experiment. Do tropical cyclones decrease in that year? So that's kind of another thing that gets used. So I'm just bringing that back in because we're going to use that in terms of looking at these paragraphs. And then thinking about like the different things that are being said in these paragraphs. So sometimes they're talking about predictions about the future, and sometimes they're talking about statements about historical trends. So that's something that we need to understand to really kind of unpack these paragraphs. And then tools for understanding is this, and then different ways to quantify these extremes are also things to keep in mind, and that will help us better understand like where some of the controversies are coming from. Is that maybe two statements sound like they're saying opposite things, but they're really in agreement because they're talking about a different way to quantify the extreme event. So just looking at this first one, revisiting it here. So there's low confidence in the attribution of changes in tropical cyclone activity. So there is kind of an implicit statement here that there are changes in tropical cyclone activity. So there's some statement about a historical trend there, but there's low confidence in the attribution, they're saying. So there's low confidence in attributing that change to increases in greenhouse gases. And the reason for that is that there's these natural cycles in ocean circulations that cause the Atlantic to get warmer and colder on decade to decade timescales. And so that could be an explanation for some of the changes that have been observed historically. So that's just, again, something to keep in mind. The point here, again, just to back up, is that I'm just trying to help you kind of notice all of the different complicated things that are going on in these paragraphs to help you better understand essentially why this is much more complicated than just than attributing global temperature change to increases in greenhouse gas concentrations. So statements about trends. So they're saying that there are trends in tropical cyclone activity. And then let's look at what else is going on. So they talk about different kind of tools for understanding. So observational evidence, lack of physical understanding. So that's this kind of basic theory. So I guess kind of multiple explanations for why a trend might occur. Low level of agreement between studies. Those are going to be mostly modeling studies they're talking about. So all of these things are going into what makes it complicated. And then, yeah, ways to quantify. So they don't mention in this paragraph what they're talking about in terms of changes, but it could be multiple ways to quantify changes. So this second paragraph that we already read, just wanted to revisit that in this framework again. So anthropogenic climate change has increased. So a statement about a historical trend. Observed precipitation. So how much it rains in a tropical cyclone. Winds, how fast the winds are, but there's low confidence in that. And then extreme sea level events, high confidence in that. So the extreme sea level events is like very straightforward because we know sea level is basically increasing globally on average every single year. But can see that there's less confidence in precipitation and winds. So that's just, okay, so that's, keep that in mind. Different ways to quantify the same thing. You have tropical cyclones. It's not just so simple as saying tropical cyclones are getting worse. Like, what does worse mean? Does worse mean precipitation? Does worse mean winds? Does worse mean number of tropical cyclones? Does worse mean, the strength when they do occur? Does worse mean how big they are? So those things can be going in different directions, and then you can get, very different statements that sound different but could be reconciled with each other. And then they talk about this other measure, poleward migration. So it could be moving in space, the average location of these things. And then they talk about historical trends in terms of the increase in the proportion of very strong tropical cyclones in recent decades. So claiming that that's been observed. And then this last one, again, same paragraph we already read, but just looking at it in terms of these types of statements. So based on process understanding, that's our, again, kind of theory for why tropical cyclones exist in the first place. And agreement in 21st century projections, so that's talking about modeling. It is likely that global frequency of occurrence, okay, so now they're talking about number of tropical cyclones, will either decrease or remain essentially unchanged. So that's a prediction. It's not saying that that has been observed in the historical past. It's a prediction based on models. So again, something to keep in mind, that's a prediction is very different than an observation of the past. And further predictions, likely increase in both global mean tropical cyclone maximum wind speed and precipitation. So different ways of quantifying tropical cyclone. And so then we're going back to frequency and intensity. So intensity could be wind speed or precipitation. Frequency is how often they occur. And then they mention process understanding, which is theory, model agreement. So modeling again. And then they talk about potentially improving understanding with model resolution increases. So again, just kind of pointing out, trying to unpack, trying to dissect these paragraphs to just point out all of the different things that are going on and what makes this complicated. So I do want to take 1 second here to talk about the ways of quantifying these things, and just talk about, there's basically 4 ways that show up in a lot of these weather and climate extreme quantifications. One is frequency, which we've already heard a number of times in these paragraphs. So that's, how many events occur, and typically you'll do it like per year. So how many times this given thing happens in a year. So how many tropical cyclones were there during tropical cyclone season in the North Atlantic in 1990, in 1991, in 1992. And so, but you do need some, you need some window of time in order to count frequency. Because if it's a day, it's like, okay, 0 on most days, like that's harder to quantify. So it's like you need a window of time, either like a year or a decade or something. Frequency. So that's one thing. And then, of course, when we're talking about like something changing in time in the context of current climate change, we're thinking about this where we're basically saying like years is we're inferring from that greenhouse gas concentrations are going up year after year. And so what's really the causal mechanism that's causing something to increase is increases in greenhouse gas concentrations. So that's just a side note, right? It's not time itself that's causing the thing to increase. It's the increases in greenhouse gas concentrations that's causing the thing to increase. Then there's intensity. So when something does occur, how intense is it? And then, of course, intensity itself could be broken down into multiple things. So we saw with tropical cyclones, it's usually wind and precipitation. Fires, it could be the spread rate of a fire. It could be the intensity in terms of carbon emitted per unit time. So it's like how much vegetation is being burned per unit time. You can get a measure from satellites of basically how hot a fire is. That could be an intensity measure. So this is where things just get complicated, and you'll see a bunch of different papers that are kind of saying, they sound like they're saying different things, but it's because they're talking about different things, and they're measuring intensity different ways. Duration. Okay, so an event happens, how long does it exist? Like a drought. So you could have a situation where droughts are not getting more frequent or intense, but they're lasting longer. So that's another thing to think about. And then size, like in terms of geographic area. So droughts, again, it could be that in some location, droughts aren't getting more frequent, they're not getting more intense, they're not getting longer, but maybe they're more extensive when they do occur. And then sometimes what happens is that you'll have, modeling being done that's, trying to model all of these different things. And the model will say, it will accurately model that, say, the frequency of something is increasing. Like this is what the model says should happen. And that is what's happening in observations here. But then the model is saying that the size of the thing should also be increasing. But then observations are going against that. And so then you're just like, it's just hard. It's hard to understand exactly what's going on. And so the point is with all of these things is that this portion of climate science is very active. It's very this is currently, there's tons of papers coming out on this stuff all the time. And it's dealing with all of these nuances and all of these different kind of conflicting pieces of evidence. And it's very different. I'm trying to delineate between the just solid, straightforward science connecting greenhouse gas concentrations to increases in global temperature, versus what's going on with a lot of these extreme events, where it's basically, like I said, it's known that there has to be temperature has to influence all of these things, just because temperature is so fundamental to all weather events. But when you start digging into the nuances of what exactly that means, frequency, intensity, duration, size, why does this model predict it should decrease, and this model says it should increase here, and blah blah blah. It's just it's very different portion of the science. It's very emerging still, and so that's why it's exciting to be a scientist in a field where there's actually things to discover. Otherwise, there wouldn't be scientists still working in that area.